Good afternoon, everybody. As William said, I'm Tom Wenisch from the University of Michigan. And I'm going to benefit enormously now from being able to follow up right after Arpit. He's already articulated much of the motivation for what I'm going to talk about here. I'm going to talk today more generically, give you kind of a history of the work that my group has done in collaboration with a bunch of folks here at the ARM, many of whom are here in the audience, on memory persistency, which is sort of a more general, thinking about how are we going to design recoverable software systems in light of the fact that we're going to now soon have byte-addressable persistent memories, just like the kinds of systems that Arpit was just talking about targeting. And with memory persistency, what we're really thinking about are the fundamental challenges of ordering writes to the persistent memory in a way that software programmers can reason formally about guarantees on the orders of those writes so that they can design algorithms that are in fact recoverable after a failure based on the evidence that's left behind in the memory system, right? And so, we came up with this term memory persistency when we first started introducing this idea, because this work is really inspired by memory consistency models that reason about the visibility of stores. Now we're reasoning about sort of visibility of stores, not to other processors in the multiprocessor, but rather visibility of stores to the recovery software. We want to make sure that the recovery software will be able to, correctly infer what happened prior to the failure. So as you can see, this is work which has actually been a series of students and also a series of collaborators at Michigan and at ARM. And so you've already seen this motivation slide, right? So why are we excited about persistent memory? Well, it's finally going to be here, right? So Intel has now promised us that cross-point 3D should happen in Q1 of next year. I think, if you pay enough money, you probably can get engineering samples now of devices that provide performance in sort of the DRAM range, density that's denser than current DRAM, and non-volatility. And so now, finally, we have a byte-addressable load-store interface to non-volatile memory, which allows us to rethink the way we're going to do software systems. So we don't just have to use a file system interface, but we can actually redesign software systems to rely on durable data structures that have fine-grained access, cache line-grained access, which might let us drastically improve performance over traditional coarse-grained block devices. So we envision, much like what Arpit talked about, that persistent memory systems will look something like this, where you'll still have a multiprocessor with a bunch of caches and a last-level cache. You'll likely still have DRAM in the system because it will still be higher performance, but alongside that DRAM we'll have a persistent memory. And now the challenge is that we want to engineer software such that when the system fails, either due to a crash or the need to reset or because power is interrupted, we're going to lose all of the state in the caches, we're going to lose the program counter and everything in the cores, and we're going to lose the contents of the DRAM, but we still have the state left behind in the persistent memory. And so that means we can have recovery software which can inspect the data structures that are left behind in persistent memory, much like databases replay logs and so on, and actually, following the restart, recover the system to a consistent state so that then regular execution can resume, and hopefully we haven't lost a lot of work. All right? So the key insight that underlies this whole investigation of persistent memory in both hardware and software approaches is the observation that recovery depends critically on being able to reason about the order in which persistent memory updates happen. And to motivate why that's the case, I just give a simple example here. Let's imagine we have a persistent linked list data structure, and we want to write code that adds a node to this linked list. So we want to fill in the node and hook it into the end of our linked list in a way that is safe. That is, where we're not going to end up with an unrecoverable state if a failure happens at any time during execution. So our initial state, we have a little linked list in memory, and we have some garbage unallocated memory space. And so in order to do this, we want to fill in that garbage memory space with the new node that we'd like to link into our linked list. And then we'd like to update the tail pointer of the linked list that now connects together the full list. And the key takeaway here is that if a failure happens during this sequence at any time, the state of the system is in fact recoverable. We might lose the forward progress of having created that additional node, but we can't be left with a state where we have garbage that's now appears to be valid data following recovery. To the contrary, however, if we were to reorder these two operations, either because the compiler decided hey, I think I can optimize by reordering these two operations. Or due to updates propagating out of the cache hierarchy in an order different from the one in which the stores were executed, if we end up with these things happening with respect to persistent memory in reverse order, well, now we've just linked a garbage node onto the end of our linked list. At the moment, there's no evidence yet in the memory system that that node is no good. And so if at this point a failure occurs, when the system recovers, we now have garbage data in what appears to us to be a valid data structure, okay? And so now this is not recoverable, all right? So the important takeaway is that if we don't have ordering guarantees that the programmer can rely on, we cannot write recovery code. There is no way to write a correct recovery code without being able to reason about the order that things happened, okay? Which now means we need the hardware to make promises to us on what reordering it's going to do and what reordering it's not allowed to do. And so we coined this term memory persistency to describe this idea of adding yet another set of ordering rules to the system stack, but now give programmers tools in the programming model that let them express constraints on the order in which writes become persistent and provide hardware implementations that then promise to obey those constraints, that either promise to enforce that write order to persistent memory or provide mechanisms like hardware logging that will recover back to the promised state in the event that a failure occurs. And as I've already pointed out, this is very similar in spirit to memory consistency models, but instead of reasoning about order of visibility, we're reasoning about the order of the moments in which memory operations become durable, okay? And a key insight underlying reasoning in this fashion is just like memory consistency, we need these models at multiple layers of the system stack. We need to have models at the ISA level, where the hardware will provide some primitives that are available to software to control and enforce these ordering constraints. But we as programmers don't program in assembly for the most part. We would like to write things in high-level programming languages. And just like we need memory models for shared memory in our higher level languages, we also need memory models for persistency in our higher level programming languages, and so we need a language level persistency model. And the role of the compiler in the runtime system is to map from a language level persistency model to the underlying hardware memory persistency model implementation in a way that guarantees the semantics of the program, and that will enable us to write portable recoverable software. So we've been working on this topic for quite some time, actually. And I'll take you through just a very brief walk through the history of what we've done in this project with our collaborators here at ARM. We first came up with this idea of let's have another consistency model back in our memory persistency paper from ISCA 2014. But that original work actually didn't propose an implementation of any persistency models at all. It simply said, hey, memory persistency should be a thing, and maybe we should reason about different orders for the way stores become visible and the way they become durable. And that raises the question, well, can you actually use these things in software? Like, is there actually some advantage to having different consistency models? So we moved on to looking sort of at the language and runtime layer, asking questions, can we provide a transactional programming interface that leverages different persistency models in a way that exposes performance differences that arise due to different semantics in different models? Of course, this still leaves the problem unsolved of actually having a hardware implementation of anything but the simplest memory consistency models. And so then we went on and delegated persist ordering to look at high performance implementations that can take some of the ideas of some of these consistency models and map them to efficient hardware. And then in our most recent work over the last 2 years, we've returned back to kind of the high-level programming interface, observing the need for language-level persistency models. In our case, we studied C++, and most recently at PLDI, and I'll give you a brief vignette about that paper here, we've proposed that synchronization-free regions might be the appropriate granularity to guarantee persistency and the atomicity of persistency with respect to the programming model. And I'll talk a little bit more about that. So I've already used a whole bunch of terminology here, but throughout the rest of the talk, when I say persist, I'm talking about that instant in time where a store becomes durable. So the persist sort of draining from the last level cache to memory or for some buffer to memory. That is the instance of the persist. And so that means in addition to traditional cache coherence memory order, we now have persist memory order or persistent memory order, which is all of the memory events in your program as ordered by the persistency model, which gives the constraints on where parts of the system are allowed to reorder those events. And so persist memory order governs the set of optimizations that are allowed in hardware and software to reorder persists. Now, there are two major kinds of guarantees that a persistency model can promise to uphold. As we've already pointed out, ordering is critical, right? We need to be able to reason about ordering, otherwise we can't write recoverable programs. And so various persistency models will give different abstractions on how to expose to programmers control over allowable reordering. However, a second dimension that we can also reason about is failure atomicity granularity. That is, which groups of stores will the hardware promise to make visible atomically? For example, in ARPIT's previous work, the entire transaction is being promised to be made persistent atomically. So if we think about the design space of ordering guarantees, in our original memory persistency work, we sort of cut this design space into two halves. By reasoning about the happens before ordering, the same kind of tool that we use to reason about consistency models. So we've divided the universe of persistency models into strict persistency and relaxed persistency. And the key idea in strict persistency is that there is no difference between the ordering rules of the memory consistency model and the memory persistency model. That is, there is only a single memory order given by the consistency model, and the hardware promises to make things durable according to the rules of the memory consistency model, which means we don't need to reason about yet another order. But there could be opportunities to optimize if instead we allow the order of consistency and persistency to diverge in relaxed persistency models. So here we'll introduce a new order which differs potentially from what would have been allowed in execution. So an example of a relaxed persistency model is Epoch persistency, which several of the folks here in the audience have actually worked on. So fences, we introduce a new kind of memory fence which breaks thread execution into epochs. We guarantee that the epochs will drain in a sequentially consistent order, but within an epoch, we allow the hardware and the software to freely reorder persist operations in any way that the hardware or software wants in order to improve performance. So, within an epoch, we can reorder these operations, and this is very useful. For example, if I'm going to write a log entry, I don't care about the order of the data elements in the log entry. I just care that the final bit that marks the log entry valid it becomes persistent after all of the individual data updates. So there's a design space of failure atomicity approaches, and in all of the ISA level persistency models to date, persistency has always been enforced at the granularity of individual instructions, and at the other end of the spectrum, we could imagine doing this at the granularity of transactions, or what I show here is at the granularity of outermost critical sections, which has the advantage for the programmer that will only see state at recovery where there aren't any locks held, and so it's guaranteed to be sequentially consistent. We don't have to worry about data races and so on. And I'm going to propose right here to actually instead reduce the burden on the implementation by providing a guarantee of atomicity at synchronization-free regions. That is, blocks of code separated by the synchronization operations. So from a programmability perspective, coarser grain is, of course, easier for the programmer, but from an implementation perspective, I need to introduce some kind of logging or other mechanism to guarantee atomicity for larger scale regions. So our most recent work proposes to reason at the synchronization-free region rather than either of the other extremes. Relative to doing this at individual instruction granularity, this is easier for the programmer. Relative to outermost critical sections, it's much less burden on the implementation, as I'll show you in the evaluation. So we have these regions of code which don't have synchronizations. Interthread ordering is provided by the synchronization operations, acquire and release. And failure atomicity will be given by the compiler and runtime system by introducing undo logging in software and then using the underlying ISA level persistency model to guarantee that the logging obeys the ordering requirements to make the logging implementation correct. The reason this is useful is that this abstraction level extends the sequential consistency for data race-free programs guarantee that we have today in our program systems like C++ to recovery code. If we didn't do this, then our recovery code might observe data races just because failure happened while we reordered a couple of operations, and now it becomes very difficult to reason about the correctness of recovery. So just briefly, how does this work? So we have a little very simple synchronization-free region here with one store in it. What the hardware or what the runtime system needs to do is introduce these 4 steps, create an undo log entry, actually modify that variable, potentially just in cache hierarchies. At some point, that variable has to become persistent. And then finally, we need to commit the log entry, that is, invalidate the log entry and indicate that we will recover to the new state, not the old state. And if we do these steps in this order, then we will guarantee recoverability. In our PLDI paper, we actually look at 2 different implementations for doing this, and I'm just going to sort of wave my hands past how these work, given the time constraint here. But if we have a very simple sequence of 2 synchronization-free regions on two threads, the simple design to how to get this right is that we do precisely those 4 steps and complete them prior to the release operation at the end of each synchronization-free region. So I'm actually going to push out log entries and actually push out the updates and make them durable before I release my synchronization variable and allow execution to move on to the next synchronization-free region. So this has the advantage that the persistent state lags execution by at most 1 synchronization-free region, so we never lose much when we fail and recover, but we pay the cost of flushing at every single release operation. We can get better performance if we observe that it's actually okay to run ahead of the durable state if we're okay on losing some forward progress. So in decoupled SFRs, we take the persist operations and the commit operations off of the execution critical path and instead allow those to happen in the background at some later point, only guaranteeing that our undo records become durable prior to actually making modifications in the cache so that if anything leaks out early, we can recover to a prior state. So decoupled SFR looks sort of like this. We're just going to create the undo log and mutate the data in the cache hierarchy. We're not going to force it necessarily to become persistent, but it could safely leak out any time. And then we'll do the release in the acquire and allow the second synchronization-free region to begin execution. And at some later point in time, we'll actually force those updates to become durable and then throw away the log records. And this requires bookkeeping to ensure that these commit operations happen in the same order that the execution actually occurred to make sure that we don't result in some inconsistent state that didn't arise during execution. And there's a lot of details in the paper on the complexity that's involved in providing those guarantees. So I'll just close with just again a brief vignette about the performance difference that you get in these various approaches. So here I'm showing you a variety of benchmarks that have been widely used in the memory persistency literature. It's normalized execution time, so lower is better on this graph. And we've normalized this graph to Atlas, which is an approach that guarantees atomicity of outermost critical sections. And we're comparing Atlas to our 2 synchronization-free region designs and to the limit of performance you would get if you don't bother flushing any data out to the persistent memory system at all, and you give up entirely on recovery. And the main takeaway that I won't go into the details here, but the main takeaway is that providing atomicity at synchronization-free region granularity instead of at outermost critical section granularity saves a heck of a lot of overhead that you need to deal with the fact that atomic regions can couple to one another across threads. And so we get a 66% performance improvement on average by avoiding all those overheads. So let me just close by, again, reiterating sort of the main takeaway, conceptual takeaways here. Memory persistency models are a new way of thinking, like memory consistency, about the guarantees that are required to make software recoverable in light of byte-addressable persistent memories. And like consistency models, we need to reason about these things at both the ISA and the language level. We can reason about different approaches to enforcing ordering, different granularities at which we could provide failure atomicity, which creates a trade-off space between performance and the burden on the programmer. And our most recent work argues that failure atomic synchronization-free regions strikes a good balance within that design space, and it gives us provably clean semantics for recovery code, the sequential consistency for data erase-free program guarantee that we're all familiar with when writing concurrent programs. So with that, I welcome your questions.
Nikos Nikolaouris from ARM Research. Thanks for the talk, it's very interesting. I would like to ask you about the differences between Atlas and your proposal, and basically where you showed some significant performance improvement, and I was wondering where those performance improvements come from.
Yeah, so the key challenge here, I can back up to the graph here, but the key challenge that Atlas faces because of the fact that it's trying to guarantee atomicity of outermost critical sections for general programs, unlike transactional approaches, you can have basically a series of critical sections that communicate with one another across multiple threads. So you'll have a coupling of the requirement to roll back a critical section across more than one thread because those two critical sections communicated with one another, but there was no point in the program in between where we dropped all of the locks. And so as a consequence of that promise to roll back all of the critical sections to a point where no locks were held, the logging that Atlas requires during forward execution has to basically communicate across threads and record all of those ordering constraints. By restricting ourselves to synchronization-free regions, we eliminate a bunch of the complexity that's required in the bookkeeping and can enable a bunch of tricks in the way we do that bookkeeping, which I'll refer you to the paper to sort of get the details on all those tricks. But it enables our sort of the logging requirements to be simpler to implement. And so really our savings here is that our logging code is much more efficient because of the fact that we don't have to worry about coupling across threads.
So do you also save on the number of writes? If you compare the volume of writes between Atlas and you?
Yeah, that's an excellent question. The simplest way to do undo logging is to sort of write every cache block, the original value of every cache block. But you can, the more freedom you have for reordering, the more coalescing can be achieved. Our compiler passes here are pretty dumb. They don't try to aggressively coalesce stuff. And so I don't recall whether our paper actually has a head comparison on the write bandwidth. But fundamentally, the difference would be whichever approach lets you coalesce more is the one that has a lower limit on the total number of writes that are needed to guarantee recovery.
Thank you.
Great talk. So Vijay Nagarajan, University of Edinburgh. So in your ISCA paper 4 years ago, you outlined the design space for persistency models, which was great. And one of the things that you talked about was strict persistency models and relaxed persistency models, where in the latter, the persistency order does not mirror the consistency order.
Yeah.
In hindsight, what do you think about is this lack of programmability in relaxed persistency models vindicated? Do you think it's necessary?
That is a really excellent question. And the evidence in the literature, including in our own work, is sort of that strict persistency is winning. Because if you think about the language level persistency models that you've been working on and that we've been writing about, they actually are all strict. They guarantee the same ordering from the C++ perspective for persistent and durable data, because asking programmers to reason about more orders is hard. That said, in sort of work going forward, we're trying to revisit this question and ask, well, maybe we can actually do a little bit better if the hardware is willing to give different ordering guarantees. Because it turns out that a lot of times, from recovery code's point of view, it doesn't care about some of the ordering constraints that really need to be upheld for multiprocessor memory consistency correctness, right? Because you're not, there's nothing else racing. There's no forward execution racing with recovery. There's only one recovery thread. And so because of that, we might not need all of those ordering constraints. So that's the high-level reason why I still believe relaxed persistency has a role, because there is that fundamental difference. But your observation nonetheless stands that most people have been working on strict persistency.
So I have a somewhat similar question. So what do the Atlas people think about the programming model implications of your work?
We'd have to go find Hans and ask him. I have, he was at the PLDI talk and he didn't look upset when he left the room. There is still a complexity here, right? The challenge is somebody still has to write the recovery code that reasons about failure at each of the synchronization operations. So what we've bought you with SFRs is we've bought you that it's data race free, because you couldn't do anything if it weren't data race free. It's just unreasonable semantics. And I think there are software systems and custom data structures where requiring outermost critical section atomicity is just the wrong trade-off. If we have, a race-free data structure or something like that, we don't want to restrict everything to outermost critical sections. I think, what is the best for the programmer? We need more experience. We need more experience writing code against each of these models to see, is it really practical to write recovery code at SFR granularity?
Thanks for all the questions. We're running out of time here.
Thank
so
you.
let's thank our speaker again, Tom.